For centuries, if a physician wanted to see inside the human body, they only had one option: a knife. The traditional anatomy lesson required a cadaver, mechanical tools, and physical destruction. To see the anatomy, you had to cut it open. Modern medical imaging replaces the knife with physics. Every modality you see in a hospital operates as a strict systems engineering matrix. First, you need an energy source. Second, that energy must interact with biological tissue in a measurable way. And third, a detector must capture that interaction and translate it into a readable data matrix. When engineers design these diagnostic systems, they are trying to check off a clinical shopping list. They want high spatial and temporal resolution, deep tissue penetration, clear diagnostic contrast, zero ionizing radiation, and fast operational speed. The underlying problem is that no single physical energy interaction can mathematically maximize all of those variables at the same time. The laws of physics force a trade-off. If you optimize for safety, you lose deep penetration. If you optimize for dense tissue, you sacrifice soft tissue contrast. Because of this physical constraint, achieving diagnostic power requires an entire arsenal of distinct imaging modalities. Each machine in a modern hospital is engineered to exploit a different set of physical laws. The most ubiquitous energy source in the hospital is the electromagnetic X-ray. A projection X-ray relies on a very simple physical interaction: photon attenuation. As the beam passes through the body, dense materials like bone absorb more photons, while softer tissues let them pass through to hit a detector, creating a shadow of varying intensities. The geometric flaw of this method is that a complex three-dimensional volume is completely collapsed into a flat two-dimensional shadow. Every structure along the path of the beam overlaps. This dimensional collapse creates a severe diagnostic ambiguity. When an entire torso is pushed flat, a subtle soft tissue anomaly, like a tumor or fluid buildup, can hide perfectly behind the dense structural walls of the rib cage or the thick muscle of the heart. Computed tomography, or CT, solves this overlapping problem. It doesn't do this by changing the physical X-ray interaction, but by applying a sophisticated mathematical solution to the recorded data. Instead of a single static flash, a CT scanner mounts the X-ray tube and detector on a gantry that rotates rapidly around the patient's axis. This captures thousands of individual planar projections from multiple angles in a matter of seconds. Using a geometric principle called the central slice theorem, an algorithm known as filtered back projection takes all of those angular shadows and reconstructs them. The overlapping ambiguities cancel out, leaving a true high-fidelity two-dimensional cross-section of the body. The modern CT scanner provides ultra-fast, high-resolution geometry. But it remains strictly limited to measuring structural density, and because it still relies on X-rays, it carries the biological cost of ionizing radiation. CT masters the mathematics of hard structural density. To visualize delicate soft tissue boundaries without the radiation cost, engineers had to abandon the electromagnetic spectrum entirely and shift to mechanical waves. Ultrasound operates on acoustic mechanics. It utilizes high-frequency sound waves rather than light to map internal architecture. The core hardware mechanism here is a transducer packed with piezoelectric crystals. These crystals convert an electrical voltage into pulsed acoustic vibrations that are transmitted directly into the body. As these sound waves travel, they encounter boundaries between different types of tissue. The detector maps the internal anatomy exclusively by measuring acoustic impedance mismatches, listening for the echoes that bounce back every time the sound hits a change in cellular density. This is a sonogram of a kidney. This physical interaction offers a massive engineering advantage. Acoustic waves carry zero ionizing radiation. This allows for completely safe, continuous observation of soft tissues. Because it is entirely safe and relies on the rapid speed of sound through water, ultrasound yields exceptionally high temporal resolution. You can track real-time physiological movements, watching the cardiac valves open and boundaries shift exactly as they happen. But the acoustic regime has a severe physical limitation. When sound waves hit a drastic impedance mismatch, like the transition from soft muscle to hard bone or from tissue to air, the wave is almost entirely reflected back toward the probe. This complete reflection creates an acoustic shadow. The sound cannot pass through the barrier, meaning everything behind it remains completely invisible. This restricts ultrasound from mapping deep tissue structures encased in bone, like the brain, or organs filled with air, like the lungs. Since mechanical waves cannot penetrate the skull, and X-ray attenuation struggles to differentiate the subtle variations between gray and white matter, mapping the central nervous system requires another physical leap. We have to move into quantum resonance. Magnetic resonance imaging, or MRI, discards the concepts of pushing high-energy photons through the body or bouncing sound waves off of it. Instead, MRI measures the intrinsic nuclear magnetic resonance of the body's atoms. Specifically, it exploits the abundant hydrogen protons inside our water and fat molecules. The hardware architecture starts with a massive, supercooled static magnet. This generates a field thousands of times stronger than the Earth's, forcing the naturally chaotic spins of those hydrogen protons into uniform parallel alignment. Inside that main magnet are the gradient coils. By deliberately altering the magnetic field strength along the X, Y, and Z axes, the scanner mathematically encodes precise spatial localization for every single voxel of tissue. Finally, the innermost ring houses the radio frequency, or RF, coils. These coils actively transmit targeted pulses of radio energy to knock the aligned protons off their axes, and then listen to the faint electromagnetic signals those protons release as they relax back into alignment. This physical process leads to the core paradox of MRI. A single machine can output radically different contrast maps of the exact same physical anatomy, without moving the patient or altering the physical structure. This is possible because MRI contrast is not a static property of density. It is an engineered product of timing. By precisely controlling the repetition time between RF pulses and the echo time when the signal is recorded, engineers dictate exactly what the final image displays. By tuning these temporal variables, the operator artificially isolates specific physiochemical properties in the tissue. This precise timing allows them to invert the brightness of gray and white matter on command, highlighting fluid in one scan and fat in the next. This extreme tunability expands MRI's capabilities far beyond simple anatomical morphology. The radio frequency signal can be deliberately sensitized to trace the random, directional diffusion of water molecules at a microscopic scale. This enables full three-dimensional tractography, mapping the exact pathways of nerve fiber bundles in the brain. The sequences can also be programmed to map in vivo temperature changes, allowing clinicians to continuously observe internal thermodynamics without inserting a physical probe. We can even isolate fluid velocity. This is a 3D MR angiography scan of the aorta. Look at the intricate pulmonary vascular structures branching off the arch. This entire network is captured solely by sensitizing the MRI sequence to the hemodynamic flow of the blood itself, without requiring external chemical dyes. This dynamic functional mapping is entirely impossible under the strictly static structural limitations of CT and projection X-ray. This complexity brings up a common operational question. Exactly how fast does an MRI take to run? The strict engineering answer is that it depends entirely on what you are querying. The speed is dictated by the sequence parameterization and the exact physical property being targeted. It can take 20 milliseconds, or it can take 6 minutes. MRI systems function as programmable quantum laboratories, querying the chemical state of a biological volume in 3 dimensions. This leaves us with a fully realized diagnostic matrix. CT maps structural density. Ultrasound maps acoustic boundaries, and MRI maps physicochemical states. To test the absolute limits of these engineered tools, we can look at this sagittal brain scan of Nobel laureate Richard Ernst. The scan captures the brain's anatomy in high resolution, but as the text points out, morphology and function are 2 entirely different things. This flawless morphological map tells the clinician absolutely nothing about the subject's intellect, his electrical activity, or his active metabolism. This is the ultimate limitation of pure morphology. A perfect structural image cannot diagnose functional physiological failure until the tissue itself is visibly degraded. This boundary represents the current focus of diagnostic engineering. The horizon of the field is the shift away from mapping static anatomy. Research is moving toward the real-time, quantitative mapping of cellular metabolism and live hemodynamics. Medical imaging has evolved from projecting the physical shadows of the dead to mathematically engineering and decoding the living signals of the human body.